All right, so in this video, we're going to finish off, we're going to continue where we left off with the dice simulation. So throwing two six-sided dice. So Z is going to be the sum of X1 and X2, where X1 and X2 are discrete uniform random variables. So they follow a discrete uniform distribution, and they go from 1 to 6. And the expected value of Z is going to be the sum of the expected value of X1 and the expected value of X2. This is going to be 3.5 plus 3.5, which is equal to 7. And this is consistent with the distribution, which we showed in our Excel file. So now I'll go to our notebook, and we will actually simulate it in Python. So let's create an array. Let's create an array of outcomes. So our dice outcomes is going to be a NumPy array. It's going to be a NumPy array of integers from 2. So it starts at 2. It says the low with the minimum value is Z of the dice outcomes. Throwing two dice is going to be the sum of the two minimum values of throwing a six-sided dice, or a six-sided die, which is B1 plus 1, so 2. And it goes up to 12. And then in Python, using NumPy, it's going to go up to, but not including the high number. So if we want 12 and including 12, we have to go to the one above it. In this case, 13. So it will go from 2 to, but not including to 13. And now let's create another array for our dice probabilities. In this one, let's just create this one ourselves. So it goes. Remember our outcomes, each one, so it's 1 and 36, 2, 36, 3, 36, 4, 5, and so on. And we add all this up together, it should be 36. And but remember, probability needs to be between 0 and 1. So let's force that to be the natural probability instead of the number of combinations a specific one has. And we have to so we're going to get an error because this is not floating point numbers. It is integers. So in order to force it to be integers, there's different ways to do it. You could just convert it to a floating point number. You could add 0, or you can divide by 1. Either one will work. It doesn't matter. They all do the same thing. And now we can look at our array of dice probabilities. We add it all up. Should be 1, and it is. So we're good there. So now we have our array of probabilities. Let's graph it out just to make sure that it's going to work. Let's create a blank figure with the fixed size. Let's go 14 to 8. Let's make it real big so we can see it. And let's do a bar chart. So the x-axis is going to be the dice outcomes, so the outcome of the random variable, and the height is going to be the probability. So our dice prob, let's look at it. So this is consistent with what it should be. And then the expected value, you can do a dot product. So NumPy dot, and we have what is it? Dice counts. I'm sorry, not dice counts. It's from before. So we have dice outcomes with dice probabilities. And this should be 7, and it is, so it checks out. This is consistent with what we did before. So now let's simulate it. Let's simulate it, and let's simulate us throwing the dice. Let's initialize a blank list. And with this list, let's throw our dice 1,000 times. Let's do a loop. So let's say for I in range, let's start at 0 and go to number of throws. So it goes up to, but not including to 1,000. So 0 to 999 would still be 1,000. The array would still be 1,000 in length. Now let's append our blank list, or our list. Let's append it with our Z. And remember, Z is the sum of the two random variables. So X1 is just going to be a NumPy dot random integer between 1 and 6. Whenever you do rand int, it goes up to, but not including the high number. So if we want to include 6, we can't put in 6 because it will not include it. We need to go one step over, which will be 7. So this would be 1 dice. We of course want 2. So we do random integer 1 to 7. And now we have it. And let's see what it will look like. And we have a list. We can't do much with a list. We have to convert it into a NumPy array. So let's do that. NumPy array, and we'll give it our list of dice throws. Now we will have it. So now we have our an array of dice throws. Now let's get our count. Let's do dice counts. Let's do NumPy.unique and a dice throw, and let's return our counts. So how many the frequency that each one occurred. Let's look at what this looks like. So we get two arrays. One is the dice outcomes. We already have this in an array. We don't need it in another one. And here's the actual frequency of which it occurred. So let's just get the second array of dice counts. Now we look at it, and it's just a frequency that it occurred. Now let's create another array. This one will be the frequency, or the frequency divided by, or the counts divided by the total. So let's do dice counts divided by dice count sum. So dice counts divided by dice count sum. Dice count sum should be equal to 1,000. Now let's look at dice frequency, or the proportion. So this isn't a frequency; it would be a proportion, and it's similar to what the probability function would show. So now let's plot it out. Before we plot it, one easy way to do it would be to just put it on a data frame. That way we can plot both of them at the same time, our proportions and our frequencies and our probabilities. So for our data frame, our data is going to be, let's do a NumPy array. Let's give it dice probabilities and our dice frequency. Let's transpose it. You can see why here in a minute. It's not necessary, but just I like the way it looks a little bit more. And let's have the index set to be outcomes, the dice outcomes. If you didn't transpose the NumPy array, then the column would have to be dice outcomes. Let's do columns equal to, let's do a probability and a frequency. Now we have our data frame. So this is the probability from the distribution. This is what we simulated. So this is the simulated values. So let's plot it out. So df.plot. I'm going to do a kind is equal to bar. Remember, the default would be line. Let's set the fig size to 14 by 8. And let's set the C map, the color map, to Viridis. And let's see what that looks like. And you can see that they are pretty close. It goes from 2 to 12. It looks pretty close to one another. And as n increases, as the number of throws increases, they are going to converge. They are going to converge. The distribution of the simulated values is going to converge to the actual probability function. So we can show that here. So instead of 1,000, let's do 10,000. And we can see that it's even closer. Instead of 10,000, let's do 50,000. You can see that it's, again, even closer than that. And as n increases, you can see it get closer and closer. So in the PDF of this, you'll see that there's a code for an animation. You can copy and paste it in the Jupyter Notebook, and you can run an animation that will go in steps of 100. And as n increases, you can see that it converges. I think it starts at 1,000 and it goes all the way to 100,000. So this is the dice simulation. And this would, if you're maybe trying to find the optimal crap strategy or something like this, then you could run simulations and try to find it. So this finishes the dice simulation. The next video will start our stock price simulation.